Hello. Today's video is going to be about modeling a nonlinear valve using a swept sine wave and Levenberg-Marquardt algorithm to minimize the sum of errors squared between the actual data and the estimated positions from the model. So what you see before you is a swept sine wave, the green control line. And you can see it only goes up to 75%, which is going to be significant later. Anyway, you start out at a low frequency and a low amplitude, and it should increase. And then as you increase the frequency, you need to decrease the amplitude so that the velocity maintains or is constant. But in our case, we ran out of hydraulic oil, so uh, we could only go up to a certain frequency. In any case, this is real data, and it's recorded every millisecond for 3.04 seconds, so it's 3,040 points of data. Now, why bother? Well, hydraulic systems hydraulic systems are sometimes nonlinear, and especially if they have a nonlinear valve, which is the case here. And you can see that this valve is very nonlinear in that you get hardly any velocity if you output up to about 2 volts. 200% is 2 volts, 1% is 10 volts. And then all of a sudden, the flow starts increasing, so you get more velocity. And this is called the deadband, where you get hardly any response for the first 20%. So this valve has got a 20% deadband. You can see that if I output 40%, I will go about 1.8, this is inches per second, in the extend direction or positive direction, and maybe about 1.7, 1.6 inches per second in the retract direction, and that's because hydraulic cylinders usually extend faster than they retract. So how do you use this data? Well, in the controller, I need to be able to compensate for the fact that this is nonlinear. So what I basically do is invert the axes or flip them around. So here you can see I got control output on this side and the velocity down here. So I know that if I want to go 4 inches per second, I can look up here and I can see that I need to output about 55% control output if I'm extending, and a little bit more, maybe 68% if I'm retracting. So this allows me to linearize a nonlinear valve. So how is this done? What I have done is I've written a control program or an optimizing program, and I wrote it in Python, and I'm using Levenberg-Marquardt or the LM-FIT algorithm to generate the or to find the minimum sum of errors squared. So the data that it generates looks like this. So now I will explain what's happening. Okay, to start with, I have this module main, and it reads data that's been saved from our motion controller. And what it does is it returns a time, so a time, a control output, and an actual position for every millisecond. And then what we're trying to do is put that into this parameter class. And Levenberg-Marquardt is a little bit more fancy than most of the uh, algorithms that they have in SciPy and the SciPy optimized modules. In any case, you give each one of the parameters a name, and you can assign it a value, initial value. This interpolation function is necessary for calculating control outputs in between the milliseconds. So I'm using a cubic interpolation. And then down here, we have the minimizer function. And what it does is it uses this differential equation part here and the parameters, and I have to give it the data, and a tolerance, and it calls this routine up above. So then I'm calculating the time. I'm printing out the elapsed time. Uh, I'm printing out the report, which is this data here. And you can see I'm printing out a mean squared error. And basically what I'm trying to do is minimize the sum of squared errors, which is this value here. And you can see it starts out pretty large at 13,000 and something. And what it's doing is it's taking a small step in each direction. For instance, it'll take the ratio value and it'll start out with a value of 0.7 and it might change it to 0.7001. And then it'll try to figure out the derivative at this point. And then it will take another step with the A1, which is one of the parameters for the differential equation. This is actually equal to the natural frequency squared. And A2 is the 2 times the damping factor times the natural frequency. This is a deadband. This is an offset. And then I have 10 gain regions. This takes care of finding the nonlinear sections of the valve. So here you can see all the initialized values. And there are 15 of them, so you have to take small increments in each direction for each of the 15 directions. It's kind of like trying to go downhill in a world where you've got 15 dimensions. And then what you're trying to do is go downhill or minimize the sum of errors squared. And you can see the first step that it takes, it goes in the right direction. And what it'll do is it'll keep on going in that direction until it's going downhill until it's no longer going downhill, in which case it stops, and then it repeats this process again. It's taking a small step in each direction in each one of the dimensions, and then it finds a new minimum. And this takes about 12 minutes to do. That's not fast. So getting back down to here, at the end, I print out the mean squared error, and the reason why I do that is that I take the sum of squared errors and divide it by the number of points. And the reason why is that there's sometimes you gather data, you might have 5,000 points or 3,000 points, and obviously the more points you have, the larger the sum of squared errors is going to be. So to kind of normalize it, I divide by the number of points to get a mean squared error or an average squared error, so I can compare sample runs of different sizes, because not all the time are the sample sizes the same. And then these last two plot routines plot the data that you saw at the beginning of the video, where I'm plotting out the valve data and the valve response. So let's move up here, and I'm plotting. This is the routine for plotting out the valve. I'm not going to go into that too much detail, but I'm plotting out the response for the different 10 different segments, gain segments. And then this plots the actual and target positions, or actual estimated positions. This is setting up the differential equations. It's doing the ODE int. There's newer integrators, but this one works every millisecond quite nicely, so I decided to use that. And what I have to do is make an initial guess for the actual position, the derivatives. So this would be the actual velocity, actual acceleration. And then this calls the differential equation. This is my model. And this is where it gets kind of tricky. What I had to do is I could use a linear model, but then that would only be good for approximating a linear valve. And so what I needed to do is find a way of finding, to fit the estimated data to the actual data. And I tried using a fifth order polynomial. I tried 2 segments, 3 segments, and the best fit that I got was using 10 segments. And what I have done is I've got a segment goes from 0 to 5%, 5% to 10%, 10% for 15%, 15% to 20%. I wanted to be very fine around the null point. Then you can see it takes larger jumps after that. So Then what it does is when I have an output, it actually sums the output from each one of the gain segments, and the gains are additive. So what happens is that you always have a gain for this 0 to 5 region, and in this example, if we take a look down here, you can see that there's um, no gains for 1, 2, and 3. In other words, this is for 0 to 5, 5 to 10, 10 to 15, 15 to 20. You can see there's nothing to add here. And each one of these gains adds to the sum of gains before that. And the reason for this is that what happens if you don't have a gain, like in our case, we don't have an output for 8%, 80% to 100%. So this is a zero, and it's just assuming that the sum of all these gains here um, continues on to the 80% to 100% range. So this is one of the tricks that I had to do to compensate for the nonlinear valve. Again, this is the mean squared error, and this is how you can tell if your fit's very good. This is if I took a particular reading, the average reading, in other words, of all these 15 points, and took the squared error between that and the actual data, the mean squared error would be, well, what is that, 4 zeros and 3 1? So 31 millionths of, well, 31 millionths. So the very end of this is I print out the time, and you can see that the time is quite long. It takes, in my case, it's over, well, it's 10 and a half minutes. That's because I've got a i7 fourth generation computer. It's not that fast, but you can see that it's going, it's minimizing in steps. It looks in 15 directions, then it goes in the direction that will minimize the sum of error squared the most until it finds a new minimum, and then it does the same thing again. And you can see that at first it drops pretty rapidly, and then it's a little bit more slow. And finally, when all the positions end up being within 10 to the minus seventh, which is my X tolerance value, let's see, where is that? That's down here, right here, 10 to the minus seventh, then it quits. And you can see that it used 193 function evaluations here. And there were 15 variables that it was trying to optimize, 3,040 data points. This chi-squared is actually the same thing as the sum of squared errors. So it said a warning uncertainties. In other words, I don't allow it to go below zero for these gains. There aren't these sections that should be zero, but these sections are close to zero. So I put a constraint on there that it shouldn't go below zero for the gain. But up here, you can see the gain can be reduced because the sum of gains will still be greater than zero. So at the end, what I end up with is this data, which has all the parameters. And then I have again, the model. This is the actual data in the cyan, and the dashed blue line or red line is the estimated data. And this is the control output, which is necessary, or the linearization table, which is necessary for the controller to linearize or compensate for the nonlinear valve. This concludes my demonstration, my video.